Webb is most sensitive to for our purposes, understanding what couldn't see before.
And what you can see is actually material falling into a black hole.
We'll continue in a moment.
James Webb is truly worth every penny. Aiming its lenses deep into the cosmos, the telescope has, for the first time, unveiled glimpses of the universe's earliest stages, capturing sharp, pristine images of the birth of stars and galaxies. These unprecedented views shed light on the formation of planetary systems, including our own. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. In the latest observation, the Webb telescope just captured a terrifying object in space, hinting the evidence of outsized black holes lurking in the distant universe. A cosmic beast formed so soon after the Big Bang that standard theory can't explain how it was built. Join us as we dig deep into how James Webb's latest discovery just shed light on the origins of invisible enigmas in deep space. Black holes, as we know, are regions of space where the gravitational pull is so strong that nothing, not even light, can escape. Rather than empty space, they are chock full of matter that gets squeezed into a teensy space. Physicist Carl Schwarzschild accidentally discovered black holes in 1916 when he was figuring out a particular solution to Einstein's general theory of relativity. He was trying to find the solution to the gravitational pull of a single, solitary, symmetric ball of matter, such as the Sun at the center of our solar system. But that solution contained a peculiar feature. The theory behaved strangely at a specific radius, known today as the Schwarzschild radius. It was later realized why this radius was so special. If you compressed the mass of an object into a space smaller than that radius, its gravitational pull would overwhelm every known force and nothing could escape. Early physicists assumed that this situation would never be found in nature. But in the late 1930s, it became clear that nature could indeed allow black holes to exist when Indian physicist Subramanian Chandrasekhar found that above a certain density, no force can overwhelm gravity. However, black holes can only form under the most extreme conditions. Stars produce light and heat due to the engines at their cores where a process called nuclear fusion occurs. There, two lightweight atoms fuse together to form a heavier atom, a process that releases energy. Those heavier atoms then fuse to form even heavier atoms, and so on to keep the star churning out light and heat. As such, when stars that are more massive than 8 times that of our Sun near the end of their lives, they fuse heavier and heavier elements in their cores, like silicon and magnesium. Eventually, they start forming iron. The problem? Fusing iron requires more energy than that reaction produces, and so at that point, nothing can counterbalance the inward gravitational pull of the star's own mass. And so the hefty star collapses in on itself. With all that crushing gravitational weight, the star's core gets squeezed beyond the Schwarzschild radius, at which point a black hole is formed. Since no known force can stop the collapse, once material forms a black hole, it keeps on squeezing down until it becomes a singularity, a point of infinite density. Surrounding that singularity is the event horizon, the invisible spherical boundary that marks the entrance to the black hole. Once anything crosses the event horizon, it can never, ever leave. In order to escape, one would have to travel faster than the speed of light, and since nothing can travel faster than the speed of light, that black hole meal is doomed. Black holes can get seriously big. Not a surprise. They're widely known to be the most massive objects in the universe. They get so big over hundreds of millions of years by both feeding on the material around them and by merging with other black holes. But it can still be a bit hard to wrap exactly how big that means. Even the littlest ones are big enough that researchers measure them in units of solar mass. A black hole that was 15 solar masses is 15 times as massive as our Sun. Supermassive black holes, the ones at the centers of galaxies, blow those black holes out of the water. The smallest ones are 100,000 solar masses, and the largest can be billions of solar masses. And it's all perfectly within the expected bounds of these mysterious gravitational monsters. Except, there's one kind of black hole that isn't quite the size astronomers believe it should be. They're ostensibly regular supermassive black holes, but they live in galaxies that seem far too young to host such massive gravity wells. Usually, supermassive black holes form over the course of billions of years, but these oddballs form over just millions. They're identified by the galaxies that host them, called outsize black hole galaxies for short. According to John Reagan, a theoretical physicist specializing in black holes, it's like seeing a family walking down the street, and they have two 6-foot teenagers, but they also have with them a 6-foot-tall toddler. That's a bit of a problem. How did the toddler get so tall? And it's the same for supermassive black holes in the universe. How did they get so massive so quickly? The prevailing theory is that these black holes are seeded, as in they come from smaller pre-existing black holes that gave them a growth jumpstart. And researchers, for the first time ever, believe that they have seen evidence of one of these seeds thanks to the ever-impressive power of James Webb. In the James Webb era, we discovered our first black holes from when the universe was less than 600 million years of age, from when the universe was just 4.3% of its current age, or younger. Specifically, we now have 3 detected black holes from that era. The supermassive black hole in the Sears 1019, which has a mass of around 9 million solar masses, about 1% of the total stellar mass at that time, which comes from around 570 million years after the Big Bang. The supermassive black hole, UHZ1, which comes from just 470 million years after the Big Bang. Although its mass is uncertain, between 10 to 100 million solar masses, the stellar mass within that galaxy is comparable. Also between 10 to 100 million solar masses, implying the black hole stellar mass ratio is at least 10% and could be even 100% or more. And the most distant black hole yet detected, in the galaxy GNZ11, comes from just 440 million years after the Big Bang. Notably, the most distant black hole itself is around 6 million times as massive as the Sun and seems to be feeding on matter from its surrounding galaxy 5 times more rapidly than the limit suggested is sustainable by current theories. University of Cambridge Department of Physics and team leader Roberto Maiolino described the discovery as a giant leap forward for black hole science. He said in a statement that, "It's very early in the universe to see a black hole this massive, so we've got to consider other ways they might form." Very early galaxies were extremely gas-rich, so they would have been like a buffet for black holes. The rate at which the black hole in GNZ11 is accreting matter could suggest that black holes may be capable of feeding much faster than other black holes discovered in the early universe have been observed to do so. This would be a leg up for small black hole seed theories. A mathematical formula known as the Eddington limit marks how fast a body, like a star, can accumulate mass without the radiation it emits, its luminosity, pushing that mass away and thus cutting off that food supply. While black holes don't emit light because they are bounded by a light-trapping boundary called an event horizon, their massive gravitational influence does cause the material that swirls around them to be violently churned and heated, emitting radiation in the process. The more rapidly a black hole feeds, the more intense the light from that region, called an active galactic nucleus, or AGN, is. Thus, the Eddington limit applies to this region, and it can similarly act to push material away and cut off a black hole's feeding frenzy. This newly discovered black hole is accreting matter from its host galaxy at a rate 5 times higher than the Eddington limit. Periods of so-called super Eddington accretion can occur, but do so in limited bouts. The team estimated that if this period of voracious feeding for this black hole had been proceeding for 100 million years, it might not have had to start life as a heavy black hole seed. It could have formed from a much lighter stellar mass black hole seed between around 250 million and 370 million years after the Big Bang, and rapidly grown to the mass it is, as James Webb observes it, 13.4 million years ago. One thing the team is fairly certain of is the intense feeding of this black hole is responsible for GNZ11 itself, which is around 100 times smaller than the Milky Way and highly luminous. But the gluttonous black hole is also likely to stunt the growth of its host galaxy. Ultra-fast winds of particles belched out from around the feeding black hole are likely to be pushing away gas and dust from the galaxy's heart. Cold clouds of gas and dust collapse to birth stars, So this means that the black hole is grinding stellar birth to a halt, in the process, killing the growth of this small galaxy. As well as learning more about this black hole and its galaxy, the team behind this research believes that the power of James Webb should help uncover more black holes in the early universe. In particular, they are aiming to discover small black hole seeds in the infancy of the cosmos and put to bed the debate surrounding the premature growth of supermassive black holes. Maiolino concluded that it's a new era. The giant leap in sensitivity, especially in the infrared, is like upgrading from Galileo's telescope to a modern telescope overnight. Before the James Webb Space Telescope came online, I thought maybe the universe isn't so interesting when you go beyond what we could see with the Hubble Space Telescope. But that hasn't been the case at all. The universe has been quite generous in what it's showing us, and this is just the beginning. In other words, with the James Webb era now in full swing, the good news is we're likely to soon find out the answer. In a recent remarkable study, by using the Webb telescope, astronomers have peered back 13 billion years to discover surprisingly lonely supermassive black hole-powered quasars. The discovery further muddies the waters when it comes to the puzzle of how some black holes grew to masses equivalent to millions or even billions of suns when the universe was less than 1 billion years old. The findings came about after a team of scientists used James Webb to study the environments of 5 of the earliest known quasars, which formed when the cosmos was between 600 and 700 million years old. The team found that the surroundings of these quasars, known as quasar fields, were surprisingly varied. Some were the densely packed environments scientists predict, but others were sparsely populated, empty larders that would struggle to feed the growth of supermassive black holes. As Anna Christina Eilers, assistant professor of physics at Massachusetts Institute of Technology, said in a statement, "Contrary to previous belief, we find, on average, these quasars are not necessarily in those highest density regions of the early universe. Some of them seem to be sitting in the middle of nowhere. It's difficult to explain how these quasars could have grown so big if they appear to have nothing to feed from." Normally, supermassive black holes may grow through progressive mergers of larger and larger black holes, models suggest. However, the problem is that this process should take over 1 billion years. But James Webb is seeing supermassive black holes that formed in way less time. It is possible to see these supermassive black holes because they sit in turbulent, gas-rich immediate environments called active galactic nuclei from which they feed. That also facilitates their growth. The immense mass of the black holes in these environments causes flattened clouds of gas and dust around them to glow brightly, often outshining the combined light of every star in the galaxy that homes them. This light, trillions of times brighter than the sun, indicates a quasar. However, supermassive black holes need a delivery service to keep their immediate surroundings well stocked with gas and dust to achieve this incredible luminosity. And it's just phenomenal that we now have a telescope that can capture light from 13 billion years ago in so much detail. For the first time, James Webb enabled us to look at the environment of these quasars, where they grew up, and what their neighborhood was like. And to investigate the wider surroundings of quasars, the team selected 5 supermassive black hole-powered regions studied by the telescope between August 2022 and June 2023. This required stitching together multiple images to create a quasar field mosaic for each supermassive black hole neighborhood. By processing the multiple wavelengths of light in the images, it was also possible to determine if the light came from a quasar's neighbor galaxy and measure how distant that galaxy originated in the bright central quasar. According to Eilers, we found that the only difference between these 5 quasars is that their environments look so different. For instance, one quasar has almost 50 galaxies around it, while another has just 2, and both quasars are within the same size, volume, brightness, and time of the universe. That was really surprising to see. The team's findings challenge the idea of supermassive black hole growth and even galaxy formation as a whole. The current understanding is that this evolution was guided by a vast cosmic web of dark matter. Dark matter accounts for around 85% of all matter, but remains effectively invisible to us. Filaments of dark matter in the cosmic web guided gas and dust in the early universe, attracting primordial matter along its vast tendrils. Where the strands of this cosmic web met, overly dense regions of matter accumulated. Here, early galaxies were built, and the first quasars should be found. The supermassive black holes situated at these nodes in the cosmic web should grow via the steady and rapid accretion of gas and dust, supplied by the cosmic web like a galactic grub hub. This would allow the quasars to achieve monstrous masses and extreme brightness. But scientists still need to know how this happened so early in the universe's history. One potential solution to this mystery is that these early quasars are actually surrounded by cosmic dust and are therefore not visible. The team now intends to tune their observations of these potentially empty quasar fields to discover any such shrouded galaxies. As Eilers concluded, our results show that there's still a significant piece of the puzzle missing of how these supermassive black holes grow. If there's not enough material around for some quasars to be able to grow continuously, that means there must be some other way that they can grow that we have yet to figure out. Notably, the evolution of early supermassive black holes isn't the only puzzle surrounding these voracious monsters. For black holes, there's a paradox which arises, as this information preservation, or increase, doesn't appear to necessarily be the case. If you throw a book into a black hole, that book contains all sorts of information: the order of the pages, the text contained on them, the quantum properties of the particles making up the pages and the cover. That information goes into the black hole, adding to its mass energy and increasing the size and surface area of the black hole's event horizon. Much later, when the black hole decays via Hawking radiation, that energy comes back out. But the information encoded in that radiation is predicted to be totally random. It's as though the book's information has been erased. Despite ongoing claims that this paradox, the information paradox, has come to an end, it still remains very much unsolved. Here's the science of what's really going on. Every particle and system of particles that exists within this universe has a certain amount of information inherent to it. Some of those properties are static, things like mass, charge, the number of baryons and leptons present, magnetic moment, and so on. But other properties are dependent on the system that it's a part of, as well as the history of its interactions. Things like its quantum entanglement properties, its spin and orbital angular momentum, and whether there are any bindings between quantum particles. If we could know the exact microstate of a system, the quantum state of every particle included within it, at any moment in time, we'd know everything that was knowable about it. Of course, in reality, that's neither physically nor practically possible. We have properties that we do know and can measure, like the temperature of a gas, and then things we not only don't know, but can't know due to the fundamental nature of quantum uncertainty, like the positions and momenta of every atom within that gas. Instead of thinking of entropy as a measure of disorder, which is misleading and incomplete, it's more accurate to think of entropy as the amount of missing information needed to determine your system's specific microstate. That definition of entropy, to think of it as the missing information that keeps you from knowing everything you'd ever possibly want to know, is key to making sense of the idea of quantum information. In our universe, to the best of our understanding, the entropy of a full physical system, including all external influences, inputs, and outputs, can never decrease. The second law of thermodynamics demands that if you take any physical system you like, and you don't allow anything to enter or leave it, then its entropy can only increase or, at best, stay the same. It can never go down. A consequence of this is that eggs can't unscramble themselves, lukewarm water never separates into hot and cold components, and fallen ashes won't ever spontaneously reassemble into their pre-combustion configuration. That's why the black hole information paradox is such a puzzle. If you take something that's full of information and throw it into a black hole, the black hole gains all of the mass, energy, charge, and angular momentum that entered it. But what happens to the information? In principle, it could get stretched out and encoded onto the surface of the black hole itself. One of the ways we can define a black hole's entropy is to do it in such a way that its surface area provides a place for every quantum of information to reside, with each Planck area of the black hole's event horizon, capable of encoding a single bit or possibly a qubit of information. But even with that additional definition of entropy for black holes, there's no known way to maintain that information eternally. Eventually, over time, that black hole will spontaneously decay, a consequence of the curvature of space-time outside the black hole's event horizon. That curvature is determined by the black hole's mass, with lower mass black holes curving space more severely at the event horizon than their larger mass counterparts. Whenever space-time is curved, it has slightly different properties, particularly for its vacuum, or lowest energy state, than when it is either less curved or flat and uncurved. It's this difference between vacuum states at different points in the space-time around a black hole that leads to something profound: the emission of radiation away from the more severely curved region. Recent research has suggested that this applies to all regions of curved space, not just for the curved space around black holes. As Stephen Hawking famously demonstrated in 1974, black holes aren't completely black, as they do emit radiation after all. That radiation has a black body spectrum, the same properties it would have if you heated a completely black, perfectly absorptive body to a specific finite temperature, where that temperature is defined by the mass of the black hole, where each quantum of radiation carries energy, which causes the black hole to lose mass via Einstein's E equals mc squared, in a process that continues at an accelerating rate until the black hole evaporates entirely. But you might notice that something is missing. This radiation doesn't seem to encode in any way knowledge of the information that went into the creation of the black hole in the first place. Somewhere along the way, information was destroyed. That's the key puzzle behind the black hole information paradox. No one seriously disputes the initial setup of the puzzle. That information exists, and that the information, and entropy, does in fact go into the black hole, both when it's first created and also as it grows. What is up for debate, and what in fact is the big question behind the information paradox, is whether that information comes back out again or not. The way we calculate what comes out of a black hole via Hawking radiation, despite the fact that Hawking radiation has been around for a full half-century as of 2024, hasn't changed all that much over the past 50 years. What we do is assume the curvature of space from general relativity. The fabric of space is curved by the presence of matter and energy, and general relativity tells us exactly by how much. We then perform our quantum field theory calculations in that curved space, detailing the radiation that comes out as a result. That's where we learn that the radiation has the temperature, spectrum, entropy, and other properties we know that it possesses, including the fact that it doesn't appear to encode that initial information when the radiation comes out. This is what we call a semi-classical calculation, where we treat the particles and fields in the universe as quantum, but we don't quantize space-time or gravity, and instead use the classical background of Einstein's general relativity to describe the space-time in which these quantum fields and particles exist. Under this semi-classical approach, as time goes on, the black hole in question loses mass, causing its radiation rate to increase until the black hole is entirely gone. So, where did all that initial information go, if it doesn't reappear somehow in the radiation that the black hole evaporates into? Something doesn't add up about all of this, clearly. But where exactly is the flaw? In general, we typically consider three possibilities. First, the information loss occurs but isn't a problem, due to some process we don't understand that allows that information loss to occur in a paradox-free fashion. Second, that even though black holes radiate like we think, information isn't lost and is somehow encoded in that radiation, meaning that we're likely drawing incorrect conclusions based on the assumptions we've made. And last, quite possibly, there's something wrong with the fundamental assumptions we've made in even formulating this paradox, and we don't understand black hole entropy correctly at all. Although the proposed solutions aren't even necessarily limited to these three possibilities, most physicists who work in this area typically expect something interesting is going on with either the second or third possibilities. There's an excellent reason to think they might be right. The space outside of a black hole is enormously complicated, even if we treat it as an idealized rather than a physically realistic system. While most of us think of space similarly to how Newton did, as an imaginary three-dimensional grid, perhaps with an additional layer of Einsteinian curvature to it. It's perhaps more accurate to think of the space around a black hole as being like a moving walkway or a river, something that moves and flows all on its own. You can walk or swim with, against, or perpendicular to the current, but the important fact is that space behaves as a non-static, in-motion entity all on its own. In addition to that, we're assuming that the laws of general relativity are still perfectly accurate for describing the dynamics of space at a quantum level. We are assuming that the quantum effects that create Hawking radiation are important, and they certainly must be. However, we're also assuming that any quantum effects that arise from treating space as a classical and continuous background, which it may not be, can be ignored. Researchers who work on this call this approach a semi-classical approximation, and the suspicion is that something about it, somewhere along the lines, must break down. But if the semi-classical approximation isn't a fully correct approach, then what is the correct way to conceive of this problem? How do we successfully perform this calculation, determining the right quantum properties for the exiting Hawking radiation, and determining exactly where that incoming information winds up when the black hole has completely decayed away? Answering those questions successfully would, in fact, provide a solution to the black hole information paradox. It's important that everyone realize, though, that despite occasional and repeated declarations from prestigious scientists and science outlets, including Quanta, who declared in 2020 that the most famous paradox in physics nears its end, those questions have not been answered at all. What has happened is indeed interesting. A series of papers and calculations have shown that when the black hole nears the end of its life, having shrunk significantly, you can no longer wall off the interior of the black hole from the outside. These effects, while negligible in our relatively young universe, will eventually dominate the dynamics of the evaporating black hole and, consequentially, the radiation that escapes from it. But this advance, like all others that have actually occurred, still doesn't answer the core puzzle of the black hole information paradox. Is information preserved? And if so, how? The 2020 article itself does a good job of diving into many of the details, including a fact that hasn't been appreciated nearly enough. When radiation comes out of a black hole, it should maintain a quantum mechanically entangled link to the interior of the black hole. That in itself is of supreme importance, as it demonstrates one surefire way that the semi-classical approximation we've used ever since the time of Hawking breaks down. Entanglement must be taken into account, including across the boundary of the event horizon. There have also been fascinating, but difficult to put into simple terms, theoretical advances that help map the entropy of the black hole's interior to the outgoing radiation, providing a suggestion that this might be a fruitful pathway toward understanding how the information gets encoded back into the universe we can access and experience. At this point, however, we're only calculating overall properties, like putting masses on a scale and seeing if they balance. We don't know what happens to the individual quanta, and how things like their individual masses, electric and color charges, baryon numbers, lepton numbers, magnetic moments, and so on, are going to imprint themselves on that radiation. Baryon number and lepton number are especially puzzling, as Hawking radiation should have a net baryon and lepton number, individually, of 0, irrespective of the initial black hole's mass, charge, and angular momentum. The questions of whether the information of an evaporating black hole is preserved, and if so, of how the information gets out, as well as the question of if that information can actually be physically gathered and measured once again, all remain as legitimate questions, all without a satisfying answer. The good news is that we've made progress on the core issue of the black hole information paradox. We can state with a fair amount of certainty that at least one of the assumptions that went into the problem, as initially formulated, is incorrect. We cannot simply look at the space outside of a black hole when we calculate the outgoing radiation. There's a continuous interplay between that radiation and the interior of the black hole itself. As the black hole evaporates, the interior begins to contain information that's linked to the outgoing radiation, and thus the black hole's interior can no longer be ignored. Unfortunately, we're still a long way away from determining exactly where that information goes and how it actually gets out of the black hole at all. Theorists disagree over the validity and soundness of many of the methods that are currently being employed to do these calculations, and no one has even a theoretical prediction for how this information should be encoded by an evaporating black hole, much less how to measure it. The black hole information paradox will no doubt be making headlines numerous times over the coming years as developments continue, but a sufficient solution to the big question of where does the information go is arguably as far away as ever.
In the vast expanse of the cosmos, where mysteries abound and the unknown stretches endlessly, the James Webb Telescope, JWT, stands as a beacon of human curiosity and technological prowess. This groundbreaking instrument, heralded as the most advanced space observatory ever created, promises to unlock secrets of the universe that have long eluded us. But what if the very discoveries it makes are so extraordinary that they challenge the foundations of our understanding? Imagine peering into the early universe and finding not just the faint glimmers of ancient stars, but objects so bright and enigmatic that they defy current cosmological models. Nobel laureates and leading astronomers are sounding alarms, describing these findings as alarming and unsettling. The implications are profound, suggesting that the universe's infancy may not align with established theories and prompting a re-evaluation of everything we thought we knew about the cosmos. What exactly has the JWT uncovered? How could these seemingly innocuous spots of light challenge the very essence of our scientific theories? As we delve into these questions, we embark on a journey that not only pushes the boundaries of knowledge, but also reveals the ever-evolving nature of science. Join us as we explore the depths of these discoveries, the theories they confront, and the future they promise to unveil. Let's look back at the day the James Webb Space Telescope launched on Christmas Day 2021, and that day that inspiration was delivered. The James Webb Space Telescope was designed and developed by NASA engineers, along with the European and Canadian space agencies. It is the largest optical telescope ever sent into space, weighing in at 6 tons and costing $10 billion. On the morning of December 25, 2021, the Ariane 5 launch vehicle's rockets ignited, causing the ground in French Guiana to tremble. The roar signaled the start of the James Webb Space Telescope's JWST month-long journey to its current home, some 930,000 miles, 1.5 million kilometers, from Earth. Although it took scientists and engineers an additional 5 months to get the 6.5-meter telescope ready for action, the wait was worth it. In the 2 years since its launch, JWST has transformed our view of the universe. It was an achievement 2 decades in the making. But in just a short year since its launch, the James Webb Space Telescope has given scientists new perspectives, amazed the public with awe-inspiring images, and opened our eyes to the infinite possibilities of the universe. Click the follow button now. We're about to uncover an astonishing truth that scientists are calling alarming and concerning. Take a look at this image. This is a newly discovered early galaxy that existed about 13 billion years ago. But researchers found that this galaxy is much larger and more mature than expected for a galaxy in the early universe. This is not the first time that Webb has found such galaxies in the early universe. Since the Webb telescope began its journey, it has challenged our standard cosmological theories. This amazing telescope is not stopping there. This time, the telescope has revealed something disturbing about the universe. Recently, a Nobel Prize-winning scientist revealed that the James Webb Telescope has finally confirmed that our understanding of the universe is completely wrong. Yes, it is not about large and bright galaxies, but this time, some new and more important observations from the James Webb Telescope have shattered long-standing cosmological theories. Consider this. One of the pillars of cosmology is that the spatial distribution of matter in the universe is uniformly isotropic. That is, everything looks the same in every direction if you look over a large enough distance. This is obvious, because the forces are expected to act equally across the universe on large scales, and therefore do not create any observable inequalities in the large-scale structure during the evolution of the initial matter field created by the Big Bang. Wherever you look, you see the same density of matter, the same temperature, and the universe is expanding the same everywhere. For more than a century, scientists have developed various cosmological models that assume that our universe is uniform in all directions. The Big Bang model, which is the best theory for understanding the universe, is also based on this assumption. The cosmic microwave background radiation also shows that the universe is the same everywhere. But a new study published on February 6 in the astrophysical journal Letters suggests that there may be something really wrong with this assumption. Astronomers have recently confirmed that the rate of expansion of our universe is not the same everywhere in the cosmos. In this paper, they reveal that depending on where we look, the universe is expanding at different rates. Now, this is a big problem because if the universe is expanding at different rates in different places, it would create a big problem for astronomers. This new study also suggests that we may be completely wrong about our current estimates of the age and nature of the universe. We wouldn't call it a tension or a problem, but a crisis, says Nobel Prize-winning astronomer David Gross. Let's dive deeper into this discovery and see how the new Webb telescope discovery confirms a crisis in cosmology. In 1929, Edwin Hubble provided the first observational evidence that our universe is expanding everywhere. Using the largest telescope of the time, he discovered that the farther a galaxy is from us, the faster it appears to be receding into space. This means that the universe is expanding equally in all directions. From this discovery, scientists thought that if the universe is expanding, then this expansion must have started at some point in the past, which means the universe must have a finite age. And since the expansion is happening equally everywhere, by precisely determining the rate of expansion, known as the Hubble constant, the cosmic clock can be rewinded and the age of the universe calculated. But before the Hubble telescope was launched, there was huge uncertainty about the rate at which the universe is expanding, or the Hubble constant, h0. This value is needed to calculate the age of the universe, estimate its evolution over billions of years, and understand the forces that drive it. When the Hubble Space Telescope was launched, it revealed that the universe could be as young as 9.7 billion years or as old as 19.5 billion years. But this younger value posed a big problem. It meant the universe was younger than the oldest known stars. Over the centuries, astronomers have used a variety of methods to measure the exact value of the expansion rate. But surprisingly, each method gives different values. It is as if the universe is expanding differently for different observations. Currently, there are two gold standard methods for finding the Hubble constant. The first method involves sifting through tiny fluctuations in the cosmic microwave background, an ancient relic of the universe's first light, created just 380,000 years after the Big Bang. Between 2009 and 2013, astronomers mapped this microwave blur using the European Space Agency's Planck satellite to infer a Hubble constant of about 67 kilometers per second per megaparsec. In the second method, we use a Cepheid variable star or supernova as a distance source. As Cepheid stars get brighter, they pulsate more slowly, giving astronomers a way to measure their absolute brightness. By comparing this brightness to the observed brightness, we can calculate the rate at which the universe is expanding. But this is where the mystery begins. According to Cepheid variation measurements, the expansion rate of the universe is about 74 kilometers per second per megaparsec, an incredibly high value when compared to Planck's measurements. Initially, some scientists thought that this discrepancy might be the result of measurement error. But recently, Adam Rees, professor of physics and astronomy at Johns Hopkins University, said, "We have now covered the entire range that Hubble observes, and we can rule out measurement error as the cause of Hubble's stress with very high confidence. In addition, new images from the James Webb Space Telescope confirm that previous measurements are correct and that the universe is expanding differently in different places. This difference in the value of the expansion rate of the universe suggests that perhaps the universe is not the same everywhere. Well, if this is true, then our standard cosmological model falls apart because we cannot estimate the age and size of the universe using different values of the expansion rate. And the most important question that arises is, why is the universe expanding differently in different places? One interesting reason could be that dark energy, the mysterious force that seems to be driving the acceleration of the expansion of the universe, is itself not uniform. In other words, dark energy is stronger in some parts of the universe than in others, causing different expansion rates. Scientists claim that if the universe is not homogeneous and isotropic, it means that the laws of physics as we understand them are incomprehensible. Just above the cosmic horizon, gravity could work in reverse. The speed of light could be slower than walking speed, and unicorns could be real. This new discovery from the James Webb Telescope has sparked a major debate among astronomers. The reason is that the uneven expansion of the universe challenges the cosmological principle, which is one of the foundations of astronomy. What do you think about the above event? Subscribe to our channel and leave a comment below. We will discuss this issue together. Now, don't take your eyes off the screen. Join us as we explore the amazing things JWT has discovered over the past 2 years. Number 1. Unveiling the Crab Nebula. Within the constellation of Taurus lies the Crab Nebula, a canvas of cosmic activity captured here through Webb's NIRCam and MIRI. The compass on the image may seem inverted because we're used to maps of the Earth, but this is the sky map and we're looking up into it. The scale here is immense, defined by light years. A distance light travels in a year, about 588 trillion miles. The light we see in this image began its journey 6,500 years ago, traversing time and space to reach us. Across this stretch, the image covers 10 light years. At the core of the nebula is a pulsar, the remains of a supernova, spinning rapidly and flashing like a lighthouse. The Crab Nebula, or M1, is not just a remnant, but a birthplace for new elements that make up planets and life. In this 5.5 arc-minute wide snapshot, we're witnessing a part of the universe's continuous cycle of death and rebirth. Isn't it a marvel how destruction and creation are intertwined in the cosmos? Number 2. The Majesty of Max 0416. Gaze at the image of Max 0416, a galaxy cluster so massive that it bends light around it. This cluster has been captured by Hubble in visible light and by Webb's NIRCam and infrared, offering a dual perspective on the same celestial marvel. The compass arrows here might seem backward, but they're not. They simply reflect the sky's orientation from our ground-based point of view. The scale is measured in arc minutes, a sliver of the sky's vast canvas, with the entire image stretching just over 2 arc minutes wide. That's a tiny angle, but it represents an immense portion of the cosmos. Known formally as Max J046.12403, this cluster lies in the constellation Eridanus. It's a gravitational lens, warping space to magnify and distort the light of galaxies behind it. It's like looking through a cosmic magnifying glass, revealing galaxies that would otherwise remain hidden. Such clusters are not just fascinating subjects for images, they're also critical to our understanding of how mass is distributed across the universe. Through Max 0416, we peer deeper into the universe's mysteries. Number 3. Max 0416 and the Marvelous Mothra. Venture into the cosmic depths and feast your eyes on Max 0416, a galaxy cluster with a special twist. This isn't just any cluster. It's a colossal cosmic magnifying glass, bending light across the eons to unveil a spectacular secret, a distant galaxy that flickered into existence a staggering 3 billion years after the Big Bang. And there's a standout star in this galactic ensemble, fondly named Mothra by the scientists, charmed by its brilliance. This isn't your ordinary star. Mothra shines with a light magnified over 4,000 times, a brilliant beacon that has traversed time and space to greet us. But what's the power behind Mothra's extraordinary glow? It's the combined might of Max 0416 and a mysterious lens, a dense celestial body with the mass of a swarm of stars known as a globular cluster. This discovery, nestled in the constellation Eridanus, is not just a testament to the wonders of the universe. It's also a thrilling clue in our cosmic detective story as we unravel the nature of the universe's hidden mass. Each glimmer in the vast dark is a story, and Mothra's is one of ancient light amplified across the ages, reaching us against all odds. What else might lie out there waiting to be magnified into view? The universe is full of such dramatic tales, and Max 0416 is just one chapter. Number 4. Webb's groundbreaking discovery, thorium from a star merger. In a celestial drama of epic proportions, Webb has struck scientific gold, or rather, thorium, detecting this rare element in the cosmos. In the grand tapestry of the universe, 2 neutron stars, remnants of stellar explosions, danced their gravitational tango in a distant galaxy before ultimately merging in a cataclysmic event. The prelude to this discovery began with 2 stars bound by gravity's inexorable pull within a spiral galaxy far beyond our own. Each star met its end in a supernova, leaving behind neutron stars, incredibly dense celestial objects. Propelled by their explosive births, these stars embarked on an intergalactic odyssey, finally colliding after several 100 million years. This violent merger set the stage for a spectacular cosmic light show, a gamma-ray burst, GRB 23307A, an explosion so powerful it shines with the light of 1,000 novas. GRB 23307A, first spotted by the Fermi Gamma-Ray Space Telescope, stands out as the second most luminous gamma-ray burst we've ever seen. Webb's infrared capabilities allowed scientists to pinpoint the origin of these neutron stars and witness the aftermath of their merger. It's here that Webb spotted signs of thorium, an element scarcer than platinum on Earth, within the kilonova glow. This marks the first time such a heavy element has been directly observed in the aftermath of a neutron star collision. The significance? Kilonovas are now confirmed as cosmic forges, where the universe's heavier elements are crafted. Webb's detection of thorium is just the beginning. Astronomers are on the brink of uncovering more secrets of the cosmos, revealing the origins of elements that construct the world around us. This discovery not only enriches our understanding of the cosmic life cycle, but also hints at the untold treasures still hidden in the vast darkness, waiting for Webb to reveal them. Number 5. The distant beacon. Unveiling a primordial black hole. Astronomers have peered across the cosmic expanse to witness a black hole from the universe's dawn. Using the keen eyes of the Chandra and Webb space telescopes, this black hole, detected through its X-ray whispers, holds the record as the most distant one we've ever seen, shining from a galaxy known as UHZ1. Such X-ray emissions are the hallmarks of a supermassive black hole feasting on surrounding material, growing larger with every bite. The black hole's story unfolds against the backdrop of the galaxy cluster Abell 2744, imaged here in infrared by the James Webb Space Telescope. This cluster, nicknamed the Pandora Cluster, is a cosmic crossroads, a gathering of galaxies whose light has traveled for billions of years to reach us. As we dive into Webb's infrared portrait, we find an ocean of darkness sprinkled with distant suns and galaxies. These dots of white, orange, and purple light are not just points, but entire galaxies, each with their own stories spiraling and stretching across the void. Among this cluster of galaxies lies an inconspicuous orange dot, seemingly modest, yet a beacon from the past. signaling from 13.2 billion light-years away. That speck houses a burgeoning supermassive black hole in the galaxy UHZ-1, a rare glimpse into the early life of such cosmic giants. This image is not just a photo, it's a window into the early universe, offering clues to how the first supermassive black holes emerged. It's a snapshot of a youthful universe, and within it, a black hole that's grown for billions of years since. It's a profound reminder of the vastness of the universe and the enduring mystery of its origins. Before JWST, astronomers thought galaxies began as small clouds of gas, dust, and stars that gradually grew into the island universes we see today. But the telescope's ability to see infrared radiation allows it to peer farther into space, and thus further back in time to when galaxies first formed. JWST has found several of these youngsters that date to within 500 million years of the Big Bang, and they are much brighter than anyone expected. The galaxies could be more efficient at creating stars than predicted, churning out massive stars at a higher rate, or most intriguingly, more massive than astronomers believed possible. Scientists also have found more advanced structures in some spiral galaxies around cosmic noon, when the universe was 2 billion to 3 billion years old and making stars at their greatest rate. In addition to making amazing discoveries, JWST also combines with other telescopes to create stunning images, like this one of the ghost galaxy M74. Early supermassive black holes. Astronomers found the most distant black hole ever detected in X-rays in a galaxy dubbed U8Z1 using the Chandra and Webb space telescopes. Everyone knows that black holes grow as they devour passing stars and clouds of gas and dust. So it comes as a surprise to find supermassive black holes, SMBHs, lurking in the early universe when they haven't had much time to chow on their surroundings. JWST has discovered several black holes, weighing about 1 billion solar masses dating to 800 million years after the Big Bang. Perhaps even more importantly, the telescope has turned up much smaller SMBHs with masses from 1 million to tens of millions of suns at even earlier times. This could provide astronomers with enough data to figure out how these behemoths evolve. Dust in the universe's youth. A young galaxy called JD's GSZ6 was recently targeted with JWST. The powerful telescope noted possible traces of molecules not expected so early in cosmic time. Dust appears all around us, in fluffy bunnies lurking under our beds, in dark clouds blocking our view of the Milky Way, and as signatures in the spectra of distant galaxies. Most dust contains carbon, so it's a relative latecomer to the cosmos because early stars had to forge the element from their initial supplies of hydrogen and helium. Yet, JWST has found dust in a galaxy just 1 billion years after the Big Bang. The dust has a unique chemical fingerprint, suggesting it may be a mix of graphite or diamond-like grains created in the earliest stars. It opens a new window into dust production and galaxy formation. Studying star formation in detail. The Rho Ophiuchi cloud complex, the closest star-forming region to Earth. Stars form in dense clouds of gas and dust. Unfortunately, dust blocks visible light, shielding much of the process from view. But the infrared radiation JWST sees penetrates dust, opening a new window into starbirth. For example, it has revealed thousands of new stars buried deep within the Eagle Nebula, M16, that Hubble couldn't reach. And JWST also showed remarkable detail in a section of the nearby Rho Ophiuchi complex. The telescope's images have revealed dozens of young, low-mass stars, as well as the jets they emit, which light up surrounding clouds of molecular hydrogen. A dusty supernova remnant. At left, supernova remnant Cassiopeia A, CAS-A, as captured by NASA's James Webb Space Telescope's NIRCam, near-infrared camera, and MIRI, mid-infrared instrument. Just 340 years ago, light from an exploding star first reached Earth. Today, we see the supernova's remnant, known as Cassiopeia A, Cas A, as a 10 light-year wide debris shell. Cas A's stunning beauty in the infrared comes from wispy tendrils of gas and the soft glow of warm dust. The dust intrigues astronomers because it is a basic building block of planets and life. They suspect most cosmic dust forms from the heavy elements supernova eject, though previous studies couldn't explain the amount of this material seen in early galaxies. Scientists hope JWST's observations of Cas A and other supernova remnants can shed more light on its creation. A jumbo surprise. The jumbios, short for Jupiter mass binary objects, discovered by the JWST. Deep in the heart of the Orion Nebula, M42, lie at least 40 planet-sized objects with a binary companion. Dubbed jumbos, short for Jupiter mass binary objects, the bodies defy all expectations. Although many stars have companions, astronomers didn't think planetary mass objects could. No star formation theory can create objects this small. And if they develop in circumstellar disks like planets do, they shouldn't be able to survive a forceful ejection. Astronomers likely will need to revise their ideas about star or planet formation or come up with a new theory for creating these jumbos. A molecular exoplanet revolution. This artist's concept shows what exoplanet K2-18b could look like based on science data. It orbits the cool dwarf star K2-18 in the habitable zone and lies 120 light-years from Earth. Although images draw the most attention, spectroscopy plays a huge role in JWST's explorations. It allows astronomers to determine the redshift and thus distance of faraway galaxies, and to analyze the chemical composition of astronomical objects. Nowhere is this more important than in the study of exoplanet atmospheres, where JWST's infrared capabilities allow it to detect molecules invisible in optical light. Among its many discoveries, JWST has found methane, carbon dioxide, and dimethyl sulfide in K2-18b, a rocky world in its star's habitable zone, hinting that it could harbor a water ocean on its surface. Rings around the Ring Nebula. NASA's James Webb Space Telescope has observed the well-known Ring Nebula in unprecedented detail. The Ring Nebula, M57, in Lyra, ranks among the sky's most beautiful planetary nebulae, the end state of sun-like stars. JWST has revealed intricate details in the ring itself, which comprises some 20,000 clumps of molecular hydrogen. But what really sets M57 apart in JWST's images is a series of 10 concentric arcs beyond the main ring's outer edge. Astronomers think the arcs first formed near the dying star when ejected gas interacted with a low-mass companion that orbits at a distance about that between the Sun and Pluto. Diving into protoplanetary disks. These Webb images show a part of the Orion Nebula known as the Orion Bar. The largest image on the left is from Webb's NIRCam, near-infrared camera, instrument. At upper right, the telescope is focused on a smaller area using Webb's MIRI, mid-infrared instrument. At the very center of the MIRI area is a young star system with a protoplanetary disk named D203506. The pullout at the bottom right displays a combined NIRCam and MIRI image of this young system. Planets form in dusty, gaseous disks surrounding young stars. JWST observations not only have provided unprecedented detail in these protoplanetary disks, but also tantalizing clues of precursors to life. Around the nearby star Fomalhaut, the telescope found 3 nested belts of warm dust, suggesting that planets shaped the disk. The observatory also detected water vapor in the inner disk surrounding PDS-70, showing that any terrestrial planets forming there would have access to water. And in the protoplanetary disk surrounding the young star D203506 in the Orion Nebula, JWST discovered the methylcation, a molecule that likely plays a key role in interstellar organic chemistry and the genesis of life. The James Webb Space Telescope has made stunning discoveries, opening up new perspectives on the dark ages of the universe. The images and data captured not only reveal the farthest corners of space, but also the current understanding of the formation and evolution of galaxies and stars. The Nobel laureate has presented the terrifying truth about what the telescope has seen, and it is truly alarming. The existence of ancient cosmic objects, including supergiant universes and previously unknown angels, raises new questions about the origin and development of the universe. This is not only a great step forward for science, but also a reminder of the mysteries that await to be solved in the not-too-distant future. Thank you for watching. Subscribe to our channel to stay updated with fascinating scientific discoveries and the mysteries of the universe. Follow us and join us on this journey of exploration.